Hello and welcome to lecture 10 part 2. In this lecture we are going to talk about calling conventions and local variables in assembly programming. Basically, a calling convention specifies standards as how a subprogram is implemented. For example, how the subprogram receives parameters and how a subprogram returns a value or multiple values, and what are the registers that needed to be unaltered or their value to be saved on the stack. And these calling convention might be different in different programming languages. Sometimes even they might be different for different compilers. Here our focus is mainly on calling convention of C programming languages. This is because we assume that for writing efficient C programs or device driver, we need to interface C with assembly, and therefore we need to know how C interact with hardware, so that when we write our assembly code, it is consistent with those conventions and rules. To understand how C calling conventions are, we can convert a simple C program into assembly and see when, for example, we want to invoke a function and define a function, what is happening, what are the exchange information between the main program and our function in here. So for this one, we assume a simple sum of functions when it uses like multiple integer as an argument, and within that function we only return the sum of those integer values. If you remember from the beginning of this course, we are able to produce the assembly equivalent of a sync function using GCC. If you use GCC, use this switch -s, and then you specify that what hardware platform you would like your assembly to be produced. So in this case, for 32-bit platform hardware, and then the type of your assembly syntax which you want, and then the name of your assembly file, and the input to this GCC command to produce the corresponding assembly file for it. So in this case, our C function our C program named call func.c. So therefore in here, we have that name. So we take this function and then we produce the assembly equivalent that function for us to understand what is happening when we invoke a function in C. So after the conversion of this C function to assembly, this is what we get. As you can see from here, we have a lot of configuration line in this our conversion, and it seems a bit cluttered for us. To get rid of those metadata in our produced assembly code, we can use a switch in our GCC function, which is given in here, to get rid of those CFI directives. So once we do that, we get a cleaner assembly equivalent of the function that is given in here. Here is where our main code is. And at this point, we call the sum function, and sum function is implemented in here. So these are the important part of the assembly code which we would like to take a look at. So we highlighted those important lines for us in the equivalent file in here. So we have our push command in here before calling the function, where we actually pass those parameters on the stack for the function using push command. And then as you can see in here, we use the EBP or base pointer to access those parameters within the stack. As you can see in our C program, we simply include those parameters in the parentheses as an argument to the function. And what is happening in practice is you call your function the label in the memory, but before going to that label in the memory, you basically push your parameters on the stack. The way that the stacks are filled up is that if you take a look at this argument in here, the last argument pushed first. So this one push first in the stack, and then next one, and so on until we move to value 2 in here. And this is going to be last one. Then we have our call assembly syntax, where we move to this label at this point. To clarify, the main is our caller in here, and the sum, we call it the callee, something that we call upon. So here is our call function. So once we call this sum and we return to this line, then we clear up the stacks, meaning that whatever we put in here on the stack, we simply point down the stack pointer to clear up these 4 elements on the stack. As you know, each element is in the stack that takes 4 bytes. That's the reason when we clear the stack, we multiply that by 4 elements by 4, and we come up with 16. Okay, in this point, let's focus on the implementation of the function only and see what happened to our stack. So as you can see in here, we said that the last element push first. That's the reason we have 10 here, 8, 4, 2. So then we call the function. The return address is going to be stored in here. And then the first thing we do in our function is push EBP. So we push EBP into the stack, and the next thing we do is to store the current value of the ESP in EBP. Therefore, our EBP is somehow now point to this point into the stack. Now, we want to access these elements, and then we simply add them together and return those values through EAX to the caller. So let's see how this can be done. In here, if you take a look at the EBP register, the value that is added to it is 8. So EBP is now pointing to this here. If we add 4 to it, we're going to get to the return address. If we add another 4, which is going to be 8, we are going to take the next value in the stack, which in our case is value of 2. We get the value of 2, we put it in EDX register, and then we get the next value in the element, meaning that we get EBP plus 12, which is pointing to 4, and then we put it in EAX register. Actually, this is what the C does. Then we add these two together, meaning that we add 2 plus 4, and the result is going to be stored in EDX register. The next thing we do is we get EBP plus 16. This time we access number 8. Number 8 is going to be stored in EAX, and what we do is to add the value of EAX to the previous two value, which now the sum is stored in EDX. Therefore, now we add these three value and the result is in EDX. The next thing we do is we access the value of D, which is 10 in this case, and we put it in EAX register. Next thing we do, we add EDX with EAX. Now the whole value, the previous three value and the 10 are added together, and the result stay in EAX register. Now when we do this, then we kind of finish the function, and then we pop EBP back, and then we return. Once it's returned, we get rid of this. Then return address is where we do that. We jump to the whatever address is pointing in here, and we discard this point, and then you're going to be stay at this point, and we go to the line after the call. Okay, so we explained this. Then okay, before we continue on the implementation of the function and see how the return value is getting into EAX and come back to the next line after the call function, I would like to have your attention on this slide where we explain different calling convention for C. So the one that we actually use in this lecture is the default C convention. We also have different calling convention for C. The other one called STD calling convention, or standard calling convention. And the next one is fast calling convention, and so on. So if you want to know more about GCC supporting calling convention, you can go to this link. And if you're interested for x86 architecture calling convention, take a look at these two links. We have a second form of the return function in assembly. So we have return immediate. So far we had only return with no argument. We also can have return immediate, where the value immediate tells us how many bytes from the stack to get rid of. You will see that an example of this return syntax in coming slide. Okay, as we talked about before, we have different calling conventions. So this is the implementation for the C declaration or default C convention, the way that we are all familiar with. And the other one is the standard calling convention that is presented in this slide. As you can see, the way that the function is prototyped is different from what we know, and the way that actually the function is defined is basically a bit different than all we are familiar with. Okay, if we convert these two C program and function into assembly, this is what we get. This is for the default one, and this is for the standard one. Let's take a look at the difference. So as you can see from here, the first part is almost the same, and we have some difference in here. And if you take a look at this, the return value in here is also different than here. we have shown these differences in here. So we don't have any line in here, while we have for the standard, for the default here. And then, as we mentioned in the previous slide, the return value are also different. In the default C convention, the return doesn't have any argument, where in the standard convention, we have some value in here as 16, which means 4 elements in the stack. And as you can see here, the function is responsible to clear up the stack, where in the default C convention, the caller is responsible to clear the stack. So these are the difference. So if you're interested to know about x86 64 architecture calling convention, you can take a look at these links. So the calling convention of 64-bit is very different from 32-bit convention. As we mentioned at the beginning of this course, when you write your assembly code, you need to know the hardware platform that your program is going to run on it. In this part of the lecture, we are going to explain how we can implement local variables in assembly. So it can be done in different ways. We can use registers, and also we can use the data segment of the code to define our local variables. So this is our C program, and this is the way that we do it in assembly. So we have our subprogram, some values defined as a double word and initialized with 0, and we have our value I defined as a double word and again initialized with value 0. Where if you have some subprogram in C, we simply use integer, sum, and I to define double word for each of these local variables. So as we mentioned in here, a data segment can be defined to can be used to define local variables. Also, data segment can be used to define global variables and stack variables. So let's take a look at the stack diagram and see where the local variables within the function can go in the stack. So if you remember from the previous template for our subprogram, we had our push EBP, then we have our move ESP to EBP. We wanted our EBP to take the relative address and the stack for us. And then here we have a new command called sub ESP number of bytes. So once you say sub ESP number of bytes, and each byte, each element in the stack, for example, is 4 byte, then by saying sub ESP, for example, 4, you make a space, one space available in the stack. And if you say ESP, for example, the sub ESP 20, then you make 5 space available in the stack, and then the stack pointer is pointing to here, and all these spaces is going to be allocated for you to use within your function. Okay, now it's a time to tell you what the stack frame is. Basically, a stack frame is part of the stack that is allocated for a given function or subprograms. It starts from where you define your parameters before calling your function, and then when you call your function, your return address is going to be saved, and you start your by pushing EBP in the stack and get the value of ESP and assign it to EBP, and then start allocating some local variable to your function. Therefore, all these place in the stack assigned for that given function, and we call it the stack frame. Therefore, we can say for each function in the stack, we have a dedicated frame. Let's take a look at the practice example and see how all these can be done. The parameters, return address, EVPs, the update, and the local variables in the stack. Assume that we have this function in C, and then the point of this function is to calculate the sum of multiple numbers that gives as an argument for us as a first argument in here, and then return that some value to the main function and printing out that value on the screen. And to do this, in our C, we define our variable A, which is going to act as a pointer within our function. And then we have our main function in here. We call our store sum 10 given as an argument, and our pointer. When we say 10, the point is to calculate the sum of the first 10 integers, 1 plus 2 plus 3 and so on until 10. We're gonna calculate this sum and store the result in our pointer A, and then we return back from the function. So the way that we implement it is this. So this is our function definition. We have our local variables defined within that function. We initialize sum with 0. We are going to use the loop and going through that loop by updating our sum for each I within that first parameter, and then we return that sum value using the second parameters in our function, which is given here as variable p. Okay, this is how the stack frame looks like for this function. So we push our first parameters on the stack, p, and then the number n, which we want to calculate the sum until that number, and then we call the function. Therefore, return address is going to be saved. We update our EBP value, and then we make some space in here in the stack, which is going to store our local variable I and sum for us. So the implementation in assembly looks like this right-hand side program. So this is going to be our assembly program, and this is what our C is going to look like. So in our assembly, as we said, when we call a function, the first thing that we do basically is to push the argument of those function into the stack. Here A, which is going to act as our pointer, and is number 10, where we want to calculate the sum for. And then we call our store sum function. Therefore, return address is going to be saved in here, and then implementation of our function happen in here. And then once we get the value back through the EAX register, then what we want to going to do is to clear up the stack using add ESP plus 8, and then finally transfer that calculated value into EAX to be printed out by our macro at this point, and then print out a new line at this point, and then we are done with the program. Okay, let's take a look at the implementation of our store sum in assembly. So as we said, we are going to we are going to store the previous value of EBP on the stack at this point, and then we are going to update the EBP value. We're gonna create some space for our local variables. In this case, only two space for I and sum, and then start doing our calculation. So the first line in here is the move command. In the move command, we say initialized basically sum with 0. Why? Because EBP now is pointing in here. The next element at the top is EBP minus 4. And the next element after that is our sum, which is pointed by EBP minus 8. So therefore, once we say EBP minus 8, and 0, meaning that initialize this location at the stack with value of 0. And then we say EBP minus 4, 1, meaning that move the value of 1 into our I location in the stack. And then we move to our for loop, where we want to add 1 plus 2 plus 3 to 10. This is what happened in the for loop. So what we do in here, we check if our I reached to the value 10, we end the loop. If not, we are going to do the sum at this point. So what we do in here, we move EBP minus 4, which is our I, updated I value into EAX register. We compare that value with EBP plus 8, which is 10 in here. And if we reach to the value of 10, we end the loop. And if not, we are going to do the sum operation. In sum operation, what we do, we take EBP minus 8, whatever value is stored in there, which is the sum, and we add it with the value of EAX, which has the current value of I at this line. Therefore, we add that, and EBP minus 8, which is our sum, is going to get the value of the sum, updated sum, and then we increment EBP minus 4, which is our I, as much as 1. Therefore, if it is 1, now it's become 2. Therefore, I, at this point, change to value 2. Then we jump to the for loop. Then we compare I with 10. If it is not as much as 10, now it's 2. Therefore, we continue the sum operation in here. So once we get to the 10 and past the 10, when I is 11, then we go to the end loop at this point. And end loop, what we do is that now we have our sum that has all these sum values, and then we are going to move EBP plus 12 to our ECX register, where EBP plus 12 is our pointer at this point, A, and then we are going to move EBP minus 8 into EAX register. What is EBP minus 8? Is our sum value. So we put it in EAX register, and then what we do, we take the content of EAX and put it in the location where it is defined by the variable A. Therefore, after that, so we take this address, we put the sum to the address pointed by A, and then we move to the next line. Next line, we say move EBP to ESP, and then we pop the value of EBP to get the previous EBP value, as we explained in the beginning of this lecture, and we return from the function. Okay, So once we put like move the value of EBP to ESP, basically our ESP is going to be pointed to here, and we kind of get rid of these two local variables in this way. Now that we know how the calling conventions are in assembly and C, and the integration of these two different languages, it is a time to talk about the enter and leave command that we have been using in our template assembly file. So what these enter and leave commands tell us. So as you know, this is our stack frame, where local variable here, EBP here, return address, and our parameters. We create the local variables using this command. We say sub ESP number of bytes, and we define that number of bytes by 4, and we get the number of elements that we have as local variables in here. So if you combine all these three arguments, so we have this one push EBP, move ESP to EBP, and now sub number of byte ESP, then you get enter command. Basically you get enter number of byte comma 0. For now you are going to accept whatever value of 0 in here. We are not going to talk about different forms of the enter command, but if you don't have the nested function, the value of the second argument in enter has to be 0. Then this is the enter that can replace all these three syntax for us, and here is the leave. Leave actually can do these two syntax at the same time for us. It is going to move EBP to ESP to get rid of the local variables, and it retrieve the value of EBP for us. Therefore, using these two commands, enter and leave, that we have in our template file before, we kind of have a shorter assembly program. Incorporating leave and enter in our functions, you will see we'll end up with less number of lines in the right hand side than the left hand side implementation of store and sum command. Here is the end of lecture 10 part 2. See you on the next video.